Hello, my name is Tony Lentz with FCT Assembly, and I am talking to you today about Fill the Void 2, an investigation into methods of reducing voiding. This is part 2 of a series of papers that we are writing and presenting on. In this paper, first we'll give you an introduction on voiding, just describing the types of voids that we're studying. Then we'll talk a little bit about the factors that contribute to voiding. And some of these factors might work together to create higher voiding levels than what you would expect. So you can't just study a single factor and expect that single factor to completely solve your voiding problem. Sometimes you might have to do multiple things to really reduce voiding. Then we'll go over the methodology or the details on how we set up our experiment, how we did this testing. After that, I'll show you the voiding results that we got. We have lots of good data to share. And from that data, I can make some recommendations on how to fill the void. Then we'll talk a little bit about future work that we're planning, that we're continuing to work on voiding and methods of reducing voiding, and we will continue to publish papers at industry events. Then I have some acknowledgments to thank my counterparts who helped work on this project. And then if you have any questions, please email me at the contact information on the title slide, or you can email support@fctassembly.com and we'd be happy to answer any questions that you have. Here are some images of typical voiding that's seen in solder joints. Here we have a typical void in a BGA ball. That's a nice spherical void. Here in the center is the type of voiding that we'll be studying. We're looking at QFN thermal pads and this type of voiding underneath the body of the QFN component. And then on the right, what we have is some pretty typical BGA voiding from a top-down view. So here's a diagram that we borrowed from the IPC 7095 standard design and assembly process implementation for BGAs. This is the only IPC standard that really addresses voiding. So this is a nice description of different types of voiding that can occur in a BGA ball. So the type of voiding that we're talking about here is void type number 1. These are called macro voids. They can be of different sizes and they can be located in different places within the solder joint. Here are some of the factors that influence voiding. Obviously, this diagram does not contain all of the factors that might contribute to voiding. There are many different things that can even work together to create voiding in a solder joint. So in general, when we studied voiding in this work, we're looking at the print dispense process. Specifically, we're looking at stencil design. In terms of reflow, we varied reflow profile. We're varying peak temp, time above liquidus. We varied silk time and temperature, and then we also varied the method of reflow. We looked at a couple different types of reflow equipment, and also studied the effects of vacuum on voiding in solder joints. And then in terms of substrate and components, we varied the surface finish of the circuit board in one of our tests, but we did not vary anything with the components themselves. And then in terms of solder paste, we did a lot of work here. We're studying 5 different solder pastes, both no clean and water soluble lead-free pastes. And then we looked at the difference in solder powder size. In one of our tests, we studied the difference between type 3, type 4, and type 5 solder powders. And then we also looked at the difference between solder powder manufacturers. Okay, here are the actual factors that we studied in this particular work. In terms of solder paste, like I said, we studied 3 different water-soluble solder pastes, 2 different no-clean solder pastes, and we took a look at solder powder size and solder powder manufacturer. In terms of stencil design, we designed a stencil with a crosshatch pattern, pretty standard window pane design. Then we took and we changed that to a 45-degree rotated crosshatch. Then we also designed a 5-dot pattern and a diagonal stripe pattern to examine the differences in stencil design and how that affects voiding. In one experiment, we looked at the difference between ENIG and OSP surface finishes and how that relates to voiding. And then in terms of convection reflow profiles, we did quite a bit of work here. We designed a ramp silk spike profile that I'm calling RSS. We had a ramp 2 spike profile, which was used for the bulk of our testing. And we also looked at the difference between reflow in air and convection reflow with nitrogen in the oven. And then we switched gears and we did some reflow in a vapor phase reflow system. And this particular system had different vacuum options. So we looked at what would happen if you use the different vacuum options and what effect that had on voiding. And then we had some boards with pre-existing voiding from convection reflow, and we tried to rework those voids by reflowing them again in a vapor phase system with vacuum. Okay, so here is the methodology that we. This is an image of the circuit board that we used. This is ENIG plating on what we call an F2A reflow board. It has 4 different QFNs for void measurement. These QFNs are at locations U9 through U12. On the right here we have a picture of the bottom surface of the QFN components that we're using. These are dummy components that have a 10mm body and they're plated with a matte tin finish. Here are the 4 different stencil designs that we used. U9 is a crosshatch pattern. U10 is the same crosshatch pattern but rotated 45 degrees. U11 is the 5-dot pattern, and U12 is a diagonal stripe pattern. You can see an image of the printed solder paste here on the right. All these QFN designs were optimized to approximately 65% area coverage so that there would be little variation in voiding due to the actual area of solder paste. Here are the 5 different types of solder paste that we tested in this study. Solder paste A, B, C, D, and E. A, B, and E are water solubles. C and D are our no clean solder pastes. All of these were made with SAC 305 alloy, and we used different solder powder sizes only on one of the solder pastes. So all these had type 3 solder powder size, with the exception of solder paste B, which we also made with type 4 and type 5 to determine the effects of solder powder size on voiding. And then on the right you can see the metal content for each one of these solder pastes is listed. And these are the standard metal contents that we would use to make up these particular solder pastes. Here's a diagram of the standard RTS or ramp to spike profile. You can see this is a smooth linear ramp up to peak. We made a high temp version of that same profile. Again, a smooth linear ramp up to a peak. The peak's about 10 degrees C higher temperature than the RTS profile, and the time above liquidus here is about 15 seconds longer than the RTS profile. Then we made a soak version of that profile. This is an RSS, ramp soak spike profile. We added some soak time here where this flat spot is between 150 and 180 C. Here's a breakdown on the stats for these 3 profiles. The ramp rate for all 3 profiles was about the same at about 1 to 1.1 degrees C per second. The soak time from 150 to 180 C was about 28 to 34 seconds for these first RTS profiles. And the ramp soak spike profile, we intentionally added time between 150 and 180 C, so we increased that up to about 80 seconds of time in that temperature range. Reflow time, or time above liquidus, for the RTS profile is about 53 to 59 seconds. The RTS high temperature profile, we intentionally added some time there. We increased that by about 15 seconds. And then the ramp soak spike profile, we tried to keep down around 60 seconds. You can see the actual measurements were 61 to 65 seconds. And then the peak temperatures were 245 to 249 C for the RTS profile. We purposely increased that by 10 degrees C to make the RTS high temp profile. And then the ramp soak spike profile was kept down around 245 C peak temp. The overall length of these profiles, the first 2 was about the same, 4.7 to 4.6 minutes, so about 4.5 minutes from 25 C to the peak. The ramp soak spike profile was a little longer than that because of that time that we added into the soak zone. Here's an image of the vapor phase equipment that we used in the vapor phase tests, and this is a diagram of what the vapor phase chamber looks like. So at the bottom we have heater plates, and above that inside the chamber is the vapor phase fluid. And then here's the vapor layer, and the circuit boards are held within the vapor layer itself. On the side walls you have thermocouples both in the fluid, the vapor layer, and then above the vapor layer. And then at the very top of the chamber there are cooling coils that help the fluid to condense, the vapor to condense and become fluid again and be recycled within the system. Here's a description of the 3 different types of vacuum that we used in the vapor phase system. So the vapor phase tests that are coded VP have no vacuum used. It's just vapor phase reflow. But the vapor phase reflow system is an oxygen-free environment. Once the vapor starts condensing over the surface of the board, it's basically protecting the solder paste from the air atmosphere. And so it is running kind of similar to how nitrogen would work in a convection reflow oven. Vacuum options that we used are coded V1, V2, and V3. V1 is main vacuum only, and the main vacuum is a two-step 5-second cycle, and it's pulling vacuum of about 750 millibar, as you can see in this diagram down at the bottom. Vacuum option V2, we're using a pre-vac number 1 plus main vacuum. So pre-vac number 1 gets pulled on the raw paste before any heating occurs, and then also main vacuum is pulled. And then vapor phase vacuum option V3 was both pre-vacs. So there's two different pre-vacs, 1 and 2 were used, plus main vacuum was used. So this option V3 uses all the available vacuum options on this particular system. So pre-vac 1 is on the raw paste again before heating occurs. Pre-vac 2 occurs during ramp up before the solder paste becomes molten. And then the main vacuum is applied while the solder paste is molten to remove gases from the solder joints themselves. Here's a diagram of the profile in the vapor phase system. So the soak time in this case is 135 to 145 C, which is a lower temperature than our soak and our convection profiles, and it's about 80 seconds long. The reflow time, or time above liquidus, is about 70 seconds, so a little longer than our other profiles. And the peak temp is only 230 C. And we can get away with a lower peak temp in the vapor phase system because the heat transfer from the fluid is much more efficient than heat transfer in a convection reflow oven. Here's a diagram of the type of data that I'm going to show. So you're going to see a lot of these kind of charts. What we have here is a box plot diagram with void area on the y-axis, and then on the x-axis are the different variables that we're looking at. In this case, this is solder paste A and solder paste B. You can see solder paste A has much lower voiding than solder paste B and a much narrower range. Here's some representative images of voiding for solder paste A and solder paste B. Both of these are water-soluble solder pastes. You can see solder paste B generates larger and much higher voiding area. On the right is a statistical analysis test that we run on the data to tell us whether these data sets are statistically different. In some cases, the data sets are very close to each other, and it's hard to tell just by eyeball whether they are different, so we run this test called a Tukey-Kramer HSD test. This is an honest significant difference test. This is done with a 95% confidence level, so this test tells us with 95% confidence that the data sets are either similar or different. And then at the very bottom, I'll be talking about these connecting letters reports. Each data set is assigned a letter, and if the letter codes are different, like in this case A and B, that means the data sets are significantly different. And then the mean values for the void area are also shown. And in this case, you can see we have 39.8% voiding versus 5.2% voiding, so obviously that's significantly different. So here are the voiding results. These are the voiding results for solder pastes that we tested in this experiment. A, B, and E are water solubles. Solder paste C and D are our two no-cleans. And these were all done with SAC 305 type 3 and the ramp to spike profile. You can see the no-cleans gave much lower voiding than the water solubles. Right off the bat, that's just generally true for most no-cleans versus water solubles in void experiments. Solder paste A looks like it gives lower voiding than the other two water solubles, and B and E are pretty similar. If we look at the Tukey-Kramer HSD test data, you can see solder paste B and E are very similar statistically, but they are much higher in voiding than A, D, and C are. We broke this data down and zoomed in on just the two no-clean solder pastes to see the difference in the pastes. So in this case, I changed the scale. This is a 0 to 10% void area scale, so we could zoom in on these box plots. Solder paste C, you can see, has slightly lower voiding than solder paste D. And if you look at the Tukey-Kramer analysis, these connecting letter reports shows that they are on different letter levels, so they are statistically different. So solder paste D generates higher voiding than solder paste C. And we're talking about 2.2% void area versus 1.4% void area. Here are the voiding results by solder powder size. So type 3 solder powder is on the left, type 4 solder powder in the center, and type 5 solder powder on the right. You can see as solder powder size decreases, void area goes down. And when we look at the Tukey-Kramer results, these are statistically significant. Type 3 solder powder gave us a void area of 53%. Type 4 had a mean area of 46%, and Type 5, 29% mean area. And this was opposite of what I expected to get out of this data. Honestly, I thought I would get higher voiding with decreasing powder size, because as powder size goes down, surface area increases, and there's more oxide present on the powder. And a general theory about voiding is that as oxide level in solder powder goes up, void area or void volume goes up. But that was opposite of what I found here. So this result's kind of counterintuitive to me. This is something that I want to look into in more detail in our future work. I'm planning on repeating this test with a different solder paste. This was done with solder paste B, a water-soluble solder paste. I want to rerun this with some no-clean solder paste and see what kind of effect the solder powder size has. This is the difference in void area for powder manufacturer. So we purchased solder powder from two different companies, Company G and Company I, and these are both SAC Type 3 solder powders. These are both made of solder paste B and the RTS profile again. You can see I solder powder has lower voiding than solder powder G. If you look at the Tukey-Kramer results, these are statistically significant. You got a 53% void area for solder powder supplier G and 37% void area for solder powder supplier I. And this is probably due to the fact that these manufacturers are making solder powder using slightly different equipment, slightly different processes, so the range of particle sizes is going to be a little different from one supplier to another, and the oxide content on the powder is going to differ a little bit from one supplier to another. Here's the voiding results broken down by stencil design. So here's the 4 stencil designs, U9 through U12, and you can see representative images of the void areas up here. It looks like U9 and U10 give relatively low void area. U11's a little bit higher. U12 again is similar to U9 and U10, but the ranges are all very similar. I mean, we're talking about 0 to 70% void area, so a wide span in the data. So this is where this Tukey-Kramer analysis comes in really handy. What we see here with Tukey-Kramer analysis, U11 is statistically higher voiding than all 3 of the other designs. And this was all run on solder paste B with the ramp to spike profile. So for that particular solder paste, U11 generated higher voiding than U9, 10, and U12. Now when we run this same test with other solder pastes, we get different results. So Stencil design needs to be matched to the solder paste that you're running. I'll present that data in future papers. In terms of surface finish, we ran one quick test with ENIG versus OSP. We have ENIG void data here on the left, OSP void data here on the right. These look pretty similar in terms of range and median value. These were both run with solder paste B, SAC Type 3, and the RTS profile. Tukey-Kramer analysis shows that these are statistically identical. In fact, the mean void area is 40.1 and 40.0% for ENIG and OSP. Now I have repeated this test with other solder pastes, and I have seen a difference in void area for OSP over ENIG. I mean, intuitively we would think OSP would contribute to higher voiding, and that wasn't the case here for this particular solder paste, but for other solder pastes that is the case, and I'll present that data again in future work. In terms of reflow profile, here's the breakdown. This is all solder paste B, SAC Type 3. The RSS profile gave slightly higher voiding than the others, so adding a soak for this solder paste increased voiding. The ramp to spike profile, you can see the void level here. We reran the ramp to spike profile 2 times on the same boards to simulate what would happen in a double-sided surface mount type of a board, which is pretty common. So the theory was, what happens to voiding on the first side that gets reflowed twice? So you can see you've got ramp to spike, and then ramp to spike run 2 times, it looks like the voiding area went up a little bit. And then the ramp to spike high temperature profile looks like it gave slightly higher voiding as well, but it's hard to tell. And then we reran the ramp to spike profile with nitrogen to see what effect a nitrogen atmosphere would have, and you can see how the voiding dropped down dramatically for this particular solder paste in a nitrogen atmosphere. Looking at the Tukey-Kramer results, the ramp soak spike gave the highest voiding level, and it was statistically similar to the ramp to spike run 2 times and the ramp to spike high temperature. The RTS profile gave statistically lower voiding than the ramp soak spike for this paste. So for this particular solder paste, we would not recommend adding a soak. That would actually increase voiding. And then run in nitrogen, you can see it dropped from the 40% void area down to 1.7% void area when run in nitrogen. That's a significant drop in voiding for this particular solder paste. Now, I wouldn't suggest that you're going to see that same dramatic drop in voiding if you run nitrogen on other solder paste. This is very paste specific. Here are the voiding results for the vapor phase system. So we ran 3 solder pastes in the vapor phase system: paste A, paste B in the center, paste C on the right. In each case, I copied in the data for the ramp to spike convection reflow. That's the blue box plot in each one of these diagrams, and that's being done for comparison to the vapor phase reflow. So for solder paste A, the ramp to spike convection profile gave roughly 5% voiding, you can see here, with a pretty wide range. Then the vapor phase reflow without any vacuum is the red box, and then the vapor phase with main vac here is the green box. So you can see for solder paste A, voiding actually went up a little bit, run in vapor phase, and then as soon as we ran vacuum in the vapor phase, it dropped down to near 0. Solder paste B, the ramp to spike convection profile gave fairly high voiding. Run in the vapor phase system, it dropped significantly. That's without vacuum. And then we ran all 3 vacuum options on solder paste B. You can see with any one of the 3 vacuum options, the voiding levels are near 0. And then solder paste C is a no-clean solder paste, and in convection reflow, it gives fairly low voiding just because of the nature of the solder paste. And then when we ran it in the vapor phase system, that actually increased voiding a little bit. But when we did vapor phase with vacuum, again, the voiding dropped down near 0 and had a very tight range. Here's the Tukey-Kramer results for these 3 solder pastes: paste A, paste B, and paste C. You can see for paste A, vapor phase was the highest voiding level. That's without vacuum. The convection profile was the median value in this case, and then vapor phase with vacuum was by far the lowest, below 1% void area. Solder paste B, the convection reflow gave the highest voiding. Vapor phase reflow dropped that down, and then when we applied vacuum, all the void areas were below 2%. Dramatic drop in void area. And then for solder paste C, vapor phase gave the highest voiding at about 14%, and then vapor phase with vacuum was statistically similar to just running it in convection reflow, 1.8% versus about 1.4% void area. So you can see that vapor phase reflow itself without any vacuum will reduce voiding just because it's an oxygen-free environment, sort of like nitrogen did in our convection profile. But when you apply vacuum, that's a guaranteed way of reducing voiding for all 3 of these kinds of solder paste. Here's the data on the circuit boards that we reworked. So these circuit boards were run first in the convection ramp to spike profile, as you can see here in this box plot on the left. Here's an image of one of the components and what the void areas look like. We reflowed those same boards again in the vapor phase system with vacuum, and the void level dropped down here. Dramatic drop in void level. And you can see here's an image of the same exact component. You can see how the voiding went from this to this. So what we see in terms of the Tukey-Kramer analysis is, of course, this is a significant difference. We had voiding mean area of about 43%, dropped down to below 9% void area. Dramatic drop. So vapor phase with vacuum or even convection reflow with vacuum could be used to rework pre-existing voids. Here are some recommendations to fill the void. We recommend use a solder paste that will generate low voiding in your process. That's very process dependent and solder paste dependent. not every solder paste will produce low voiding in every type of process, so you've got to pick the right solder paste to use in your process. We recommend that you switch from type 3 to type 4 or type 4 to type 5 solder powder in order to minimize voiding. And you also get a print benefit from doing that. Now, type 4 solder powder is becoming fairly standard in the industry. I see very few people using type 5. Type 5 solder powder carries an added cost with it, and it also has a shorter shelf life typically, so this would be more of a switch if you're having, say, print issues rather than for voiding. But just keep this in mind. If you're thinking about switching from type 3 to type 4 for print issues, it may also have an effect on the voiding levels if that's important to you. We highly recommend you design a stencil to give gas escape routes. We know that underneath QFNs and other bottom terminated components, voiding is a big potential concern. You have to do something with stencil design, not only to minimize solder paste volume to reduce float of the component, but you've got to give some kind of gas escape routes for the gases to get out from underneath that component. Otherwise, your voiding levels are going to be pretty dramatically high. The reflow profile itself has to be tuned for the solder paste that you're using. As you saw in our data, adding a soak to the profile increase voiding for some of the solder pastes and not for other solder pastes. So you have to tune your profile to minimize voiding for your solder paste in your process. We recommend that you use an oxygen-free system for reflow. That had a dramatic effect on voiding in our testing. You can do that using certain vapor phase equipment or by using nitrogen in your convection reflow oven. And then finally, using a reflow system with vacuum had a dramatic effect on voiding regardless of solder paste. So regardless of solder paste type or even the way the profile is set up, if you apply a vacuum to the liquid solder joint, it's going to reduce voids, guaranteed. So here's some of the future work that we've started on and that we're planning for our next paper. We're going to run some additional component designs like some LGAs and some BGA components, and we might include some LEDs in future work. We're going to test different stencil designs, continue to work on that to see what effect the stencil design can have for each solder paste that we use. And then we're also going to do some additional work on solder powder size and oxide levels. So we're going to repeat this testing with type 3 versus 4 and 5 solder powders with different types of fluxes to see what effect that has on voiding. We're going to repeat testing on surface finish impact. I want to rerun OSP versus ENIG with different solder pastes because I know OSP will have an effect on void levels. We're also going to repeat testing on the nitrogen and convection reflow with some alternate solder paste to see if the effect is just as dramatic as what we saw with solder paste B in this test. And then lastly, I want to run void testing over the stencil life of the solder paste. I want to see what happens, say, over an 8-hour workday, especially with water-soluble solder paste in a humid environment. What happens to the void level? The water-soluble solder pastes absorb moisture out of the air over time, and in a humid environment that's accelerated. Moisture in the solder paste obviously is going to turn into a gas during reflow, and that should increase voiding levels. But I'm going to prove that out by running the test and gathering the data. I would like to thank my colleagues at ATEC Systems for their support, helping to co-author this paper and running all the vapor phase reflow testing. Thank you. I appreciate your time and attention listening to this presentation. And if you have questions, like I said earlier, please email us or give us a call, and we'd be happy to share any information you'd like with you. Have a great day.